Hi guys, we'll talk about molecular shapes today. And this is explained by the theory that is named VSEPR. What does it mean? VSEPR means balanced shell electron pair repulsion theory. And it's fundamental to understand how are distributed the electrons in the space. Okay, the electrons in the space will determine also how are distributed the atoms in the space. Here we have to begin with Lewis structures. So we have to begin with the Lewis structure that we already know how are they drawn, and then go ahead and make the 3D structure of it. The general model in which we will use this VSEPR theory is the ABX model. Okay, this model means the A for the central atom, B for the surrounding atoms, and X is the number of surrounding atoms. For this theory, we'll have another concept, the electron domains and the molecular domains. Electron domains are is a lone pair, a bond. A bond can be understood as a single, double, or triple bond that are around the central atom. Those are the electron domains. For instance, if we have a molecule that has in the central atom two double bonds, we'll have an electron domain of 2. Molecular domains is the number of atoms that are surrounding the central atom. Okay, this is easier. So here we have an example of different ions and molecules that have different number of beaks according to the central atom surrounding the central atom. So an AB2 molecule will have always a molecular domain of 2, an AB3 a molecular domain of 3 because, for instance, the boron fluoride will have 3 fluorides surrounding the boron. Okay, AB4, AB5, AB6, each of those have the same number of molecular domains as the same number of bees. So, for instance, phosphorus fluoride, that is here, will have a molecular domain of 5. How is the electron domain? The electron domain is different. Remember that it's the number of bonds that are attached to the central atom or the number of lone pair electrons attached to the central atom. Here, for the carbon dioxide, we have 2 double bonds around the central carbon. We will have 2 electron domains. And for the ammonia, we will have 1, 2, 3 bonds and 1 lone pair electrons. So that means that we have 4 electron domains. That is the same for all of them. For instance, selenium fluoride will have 1, 2, 3, 4 bonds and 2 lone pair electrons. If we add those together, we'll have that we have 6 electron domains. That is the way how we will determine these parameters. Whenever the electron domain is equal to the number of molecular domains, we'll have these shapes. So the first one will have an AB2 molecule, so with a number of molecular domain of 2 that has also 2 electron domains. So will be a linear molecule in which both are with an angle. The distribution of this in the space will be with an angle of 180 degrees. In the second case, we have an AB3 molecule with 3 electron domains. This is named as trigonal planar shape. Here we have an AB4 molecule with 4 molecular domains with 4 electronic domains. This is named as tetrahedral. Here we have 1, 2, 3, for five molecular domains and 5 electron domains named as trigonal bipyramidal, and finally 1, 2, 3, 4, 5, 6 atoms surrounding the central atom with 6 electron domains will name as octahedral shape. Okay, the electron domain geometry is the distribution of different electron domains in the molecule, and the molecular geometry is the distribution of bonded atoms in the molecule. Okay, so from electron domain and molecular domains, we will move to a concept that is the electron domain geometry and the molecular geometry. Why is it important? Okay, in some molecules, the number of electron domains are different from the number of molecular domains. So this is the table for those kind of molecules. This kind of molecules are, for instance, the H2O, the water, the central oxygen, have 2 lone pairs, okay, lone pair electrons, and it has, two molecular domains that are 2 hydrogens. Pardon me. So we will have for the electronic domains a tetrahedral shape, okay, the electron domain geometry tetrahedral, but the molecular domain that will determine finally the shape of the molecule, because the atoms are those that are seen in the molecule, will be a molecule known as bent, just bent. Okay, and take a look to the iodine fluoride. Iodine fluoride. So we will have a molecule with 2 molecular domains. Okay, just 2 molecular domains, and electronic domains. We have 1, 2, 3, 4, 5 electronic domains. So the electrons are distributed in a trigonal bipyramidal way, but the atoms here will be distributed as linear. Okay, linear molecule. Got it? Here we have selenium fluoride, for instance. It will have, for the molecular domain, it will have just 4. 1, 2, 3, 4 molecular domains. But for the electron domains, we will have 1, 2, 3, 4, 5, 6. How is that shape name? Octahedral. So the lone pair electrons will be in the upper and lower part, while the bonded atoms will be around it. It will form a square planar shape. This is another table that is more complete, just showing those situations in which we have 2 bonds, non-lone pair electrons. So we have an AB2 molecule with no lone pair electrons, so the electron domains are the same as the molecular domain, and we will have a linear molecule with 180 degrees. It's just another table that includes also the those molecules that have the same molecular domain and electronic domain. Okay, here is an example of an application of that kind of theory. This kind of theory is very useful to create, for instance, medicine and vaccines. Okay, here in an article from Manuel Arroyo, we will see that we have different major major human complex, okay, that can attach to different antigens, okay, that are designed by the laboratory. They have some specific shapes that allows the molecule to be attached to the MLA complex, the major immunity complex. Here, the joint will determine if a monkey can be immune to the response to malaria. So it's very important for the advance of science just knowing the shapes of the molecule. Okay, here we have enough time in this video, or don't worry, or in another video we will see how are the molecule shapes determined in a program. So here is a page that is named as PHET for the Colorado University that allows us to make many simulations. So we have this program that is named Molecule Shapes. Please go ahead, search it, and play with it. We have the model here. So we have a central atom. We put 1, 2 bonds, and we will have the linear molecule. This is a model, it's not a real molecule. Okay? If we add another atom, we will have the trigonal planar shape with 120 degrees. Okay? Between each of the bonds. We have another atom, we will have the tetrahedral shape, and its angle is 109.5 degrees. Another bond will have the trigonal bipyramidal shape. In this case, we'll have two kinds of angles. One of them is of 90 degrees. The other one, if I'm able to see it, is of 120 degrees. Okay, this one here between these two atoms. And if we add the last atom, we will find that we will have the octahedral molecule, in which all the atoms are bonded by an angle of 90 degrees, are distributed in the space as that. But what happens whenever we add lone pair electrons? Let's suppose that we have an AB2 molecule, but the molecule has a lone pair electron. So let's put the lone pair electron, take a look at it. The lone pair electrons will push the bonded electrons towards the lower part. Why? Because they make a repulsion here. Okay, the shape will be a distribution of the atoms here of 120 degrees. Okay, if we add another lone pair, we will see that the angle is 100 and 109.5 degrees. Why is it happening? Okay, the electrons are distributed in a tetrahedral shape, while the atoms are just bent. But these lone pair electrons will push the atoms to be joined together than just being 180 degrees. Okay, so we can have a more complex molecule. Just adding another atom. Take a look at it. It's not in a, it's just in a plane, but whenever we add a lone pair electrons, this lone pair will push those electrons that are bound lower. Okay, will make a shape of 109.5 degrees. Okay guys, let's continue in the other video.